Hello my friends, and welcome back to KrossUSA channel. Today, we're taking you inside operations, processing 60,000 cubic meters annually, where century-old craftsmanship meets space-age technology. From towering mountain pines to precision-engineered lumber, witness the incredible journey of American timber through cutting-edge mills that would astound the pioneers who built this nation. You know, there's something deeply American about the sight of towering timber stretching across mountain slopes. It's a view that's defined our nation's character for generations. Today, we're taking you on a journey that begins high in the rugged terrain, where skilled loggers continue a tradition that built America, using modern machinery that would astound the pioneers who first cleared these very hills. And our story starts on steep mountain slopes where specialized harvesting equipment tackles what gravity makes challenging. These aren't your grandfather's chainsaws and crosscut saws, though the spirit of those early lumberjacks lives on in every cut. The modern feller buncher, weighing in at around 65,000 pounds, moves through the forest with surprising grace. Its hydraulic cutting head can slice through trees up to 24 inches in diameter in mere seconds, accumulating multiple trees before laying them down in organized bunches. You know, the evolution of tree harvesting tells a remarkable story of American ingenuity. Back in the 1800s, lumberjacks, they called themselves timber beasts, would spend an entire day felling just one massive pine using crosscut saws and axes. These men were legends in their own right, with names like Paul Bunyan becoming folklore. The introduction of the chainsaw in the 1940s revolutionized the industry, but even those early chainsaws weighed over 100 pounds and required 2 men to operate. Today's feller bunchers represent the culmination of over a century of mechanical evolution, incorporating GPS technology that allows operators to map every tree harvested for sustainable forest management. What's fascinating is that modern hydraulic systems operate at pressures exceeding 5,000 psi. That's enough pressure to cut through steel. Yet these machines are so precisely controlled that an experienced operator can pick up a single branch without disturbing the surrounding vegetation. What's fascinating is how these machines have evolved from the days when lumberjacks would spend hours on a single massive pine. The feller buncher's operator sits in a climate-controlled cab, using joystick controls that would feel familiar to anyone who's operated heavy equipment, yet the precision required takes years to master. Each tree must be carefully analyzed, its lean, the surrounding terrain, and the safest direction for it to fall. But here's where it gets really interesting: getting those trees down the mountain. In the old days, they'd use log drives down rivers or build temporary railroads. Today's solution is equally ingenious, but far more efficient: the cable yarding system. Picture this: a massive steel tower, sometimes reaching 100 feet high, anchored securely at a strategic point on the mountainside. From this tower, steel cables, some as thick as your thumb, stretch across the terrain like a giant spider web. NNTHE main skyline cable, tensioned to support tremendous loads, serves as the highway for logs traveling downhill. A carriage system runs along this cable, controlled by a skilled operator who can position it anywhere along the span. The chokers, that's what we call the cables that wrap around the logs, are set by workers who know these mountains like the back of their hands. When everything's ready, the yarder engine roars to life and dozens of logs begin their aerial journey down the mountain. At the landing, it's like watching a well-choreographed dance that's been perfected over decades. The loader, a specialized machine with a knuckle boom crane, sorts and loads the logs onto logging trucks with mathematical precision. These aren't just any trucks. They're purpose-built giants capable of hauling 80,000 pounds when fully loaded. The trailer design, with its multiple bunks and securing systems, ensures that precious cargo reaches its destination safely. NTHE Journey from Mountain to Mill tells the story of American ingenuity, from the GPS systems that help drivers navigate winding mountain roads to the communication networks that coordinate every aspect of the operation. As these trucks roll toward the Idaho Forest Group facility in Grangeville, they're carrying more than just timber. They're carrying a renewable resource that will become the homes, furniture, and countless products that define American craftsmanship. Welcome to Grangeville, Idaho, where the Idaho Forest Group operates one of the most sophisticated sawmill operations you'll find anywhere in the American West. This isn't just a sawmill, it's a testament to how traditional American craftsmanship has evolved to embrace cutting-edge technology while staying true to the principles that built our nation's lumber industry. NTHE Idaho Forest Group has deep roots in the region, representing the kind of family-owned enterprise that's been the backbone of American industry for generations. Their Grangeville facility processes primarily ponderosa pine, Douglas fir, and grand fir, species that have been providing building materials for American homes since the frontier days. But what happens here today would seem like magic to those early millworkers. NTHE history of sawmilling in America is deeply intertwined with our nation's westward expansion. The first water-powered sawmill was built in Jamestown, Virginia in 1607. But it was the development of circular saw technology in the 1810s that truly revolutionized lumber production. Before circular saws, mills used up and down saws that could only make one cut at a time, processing maybe 1,000 board feet per day. The transition to circular saws increased production tenfold. What's particularly interesting about the Idaho Forest Group's approach is their integration of European precision machinery with American production philosophy. The laser scanning systems they employ use technology originally developed for the aerospace industry. The same principles that guide missiles can measure log defects to within 1/32nd of an inch. Modern bandsaw blades, which can be over 30 feet long, are manufactured from Swedish steel and undergo a specialized heat treatment process that creates micro-hardness variations across the tooth profile. This allows the blade to stay sharp longer while resisting the tremendous stresses of cutting through frozen logs in winter conditions. The sawmill's computer optimization systems process over 50 different variables for each log, including species, moisture content, grain angle, and even local market prices, making cutting decisions in milliseconds that would take a human sawyer minutes to calculate. And as our logging trucks arrive at the mill, they encounter the log deck, a staging area that's the nerve center of the entire operation. Modern mills like this one use computerized log sorting systems that scan each incoming log with laser precision. These systems measure diameter, length, and even detect internal defects using ultrasonic technology that's similar to medical imaging. It's remarkable. A process that once required the trained eye of an experienced sawyer can now be accomplished in seconds by sensors that never get tired or make subjective judgments. NTHE heart of any sawmill is the head rig, and IFG setup is a marvel of engineering efficiency. The logs move into position on the carriage, a massive contraption that's evolved from designs that date back to the 1800s. But today's carriage systems are controlled by computers that calculate the optimal cutting pattern for each individual log. The bandsaw blade, a continuous loop of steel with teeth that are precision sharpened, slices through logs with a whistle that's become the signature sound of American lumber production. What's fascinating is the decision-making process happening here. Every cut is planned to maximize the value extracted from each log. The computer analyzes the log's characteristics and determines whether it should become 2x4 studs for home construction, 2x8 joists for floor systems, or perhaps specialty lumber for custom applications. This optimization process, what we call sawing for grade, can increase the value derived from each log by 15 to 20% compared to traditional methods. After the head rig makes the initial cuts, the cant, that's the squared up section of the log, moves to the gang edger. This machine uses multiple circular saw blades to make simultaneous cuts, transforming the cant into several pieces of dimensional lumber in a single pass. The precision here is measured in thousandths of an inch, tolerances that ensure lumber will meet the exacting standards required by modern construction. NBUT, the magic really happens at the trimmer saws. Here, pieces are cut to exact lengths while defects are removed with surgical precision. Operators with decades of experience work alongside automated systems that use optical scanning to identify knots, splits, and other characteristics that affect lumber grade. Each piece is marked with a grade stamp that tells the story of its quality, a system of standards that's been protecting American consumers for over a century. NTHE sorting and stacking systems at IFG represent the culmination of generations of lumber handling innovation. Automated stackers build perfectly aligned packages of lumber with stickers, thin strips of wood placed between each layer to allow air circulation during the drying process. These packages, or lifts as they're called in the industry, are then moved to the dry kilns. NTHE kilns themselves are marvels of controlled environment technology. Modern lumber drying has moved far beyond simply air drying lumber in stacks. These computer-controlled chambers manage temperature, humidity, and air circulation with the precision of a fine watch. The drying process, which once took months in natural conditions, can be completed in days while ensuring consistent moisture content throughout each piece. The science of lumber drying represents one of the most sophisticated aspects of wood processing, involving principles of thermodynamics, materials, science, and even nuclear physics. Early American sawmills relied entirely on air drying, which could take 6 months to 2 years depending on the species and thickness. The first kiln drying experiments began in the 1860s, but it wasn't until the 1920s that reliable kiln drying became widespread. Modern kilns use a process called conditioning, where steam is introduced at specific intervals to relieve internal stresses that develop as wood loses moisture. This prevents the checking and warping that plagued earlier drying methods. What's remarkable is that the kiln schedules, the precise temperature and humidity curves used for each species, are based on decades of research into wood cellular structure. Douglas fir, for example, has a cellular structure that allows rapid moisture movement, so it can be dried at higher temperatures. Ponderosa pine, with its resin-filled cells, requires gentler treatment to prevent resin bleeding. The most advanced kilns now use radio frequency technology, similar to microwave ovens, to heat lumber from the inside out, reducing drying time by up to 50% while producing superior results. Quality control at facilities like IFG involves multiple checkpoints where both human expertise and machine precision work together. Graders trained in the subtle art of lumber evaluation examine random samples, ensuring that every piece leaving the mill meets or exceeds industry standards. This commitment to quality reflects values that have been central to American manufacturing since the earliest days of our Industrial Revolution. Now let's journey into the world of engineered wood products with Plum Creek Timber, a company whose story is woven into the fabric of American forest products history. While traditional sawmills transform logs into dimensional lumber, Plum Creek's specialty lies in creating engineered wood products that have revolutionized modern construction and furniture making. Plum Creek Timber has been a cornerstone of American forestry for decades, managing millions of acres of timberland and pioneering sustainable forest practices that ensure these resources will be available for future generations. Their approach to manufacturing represents the evolution of wood utilization, taking smaller trees, wood chips, and even sawmill byproducts and transforming them into products that often outperform traditional solid wood. The development of engineered wood products tells a fascinating story of American innovation born from necessity. During World War II, when high-quality lumber was desperately needed for aircraft construction and military facilities, researchers began experimenting with ways to use lower-grade wood more efficiently. The first commercial MDF was produced in the United States in 1966, but the technology traces back to experiments conducted at the Forest Products Laboratory in Madison, Wisconsin during the 1940s. What makes MDF remarkable is that it's actually superior to solid wood for many applications. It doesn't have grain direction, so it won't split when screws are driven near edges, and it machines to incredibly smooth surfaces. The resin systems used in modern MDF production are marvels of polymer chemistry. The urea formaldehyde resins cure through a process called polymerization, where small molecules link together to form long chains that create incredibly strong bonds. The pressing temperatures of 400 degrees Fahrenheit aren't arbitrary. This is the precise temperature needed to activate the resin catalyst while driving off moisture without scorching the wood fibers. Modern MDF plants use continuous presses that can be over 40 feet wide and operate 24 hours a day, producing panels with density variations of less than 5% across their entire surface. The environmental benefits are substantial. MDF production uses wood that might otherwise be burned as waste, and modern plants achieve thermal efficiency rates exceeding 85% by using their own wood waste as fuel. Let's start with their MDF production. That's medium density fiberboard, for those who might not be familiar with the term. MDF represents one of the most ingenious uses of wood fiber ever developed. The process begins with debarked logs that are too small or have too many defects for traditional sawmilling. These logs are fed into massive chippers that reduce them to uniform chips about the size of a silver dollar, NBUT. Here's where the science gets fascinating. Those chips are then processed through refiners, machines that use tremendous pressure and heat to break down the wood fibers to their individual components. Steam at temperatures reaching 300 degrees Fahrenheit softens the lignin. That's the natural glue that holds wood cells together. This process literally returns the wood to its basic building blocks. NTHE refined fiber is then combined with specially formulated resins and waxes. The resin system is crucial. It determines the final product's strength, moisture resistance, and machining characteristics. Modern MDF uses urea formaldehyde resins that create incredibly strong bonds when activated by heat and pressure. The mixture is carefully controlled, typically 82% wood fiber and 12% resin, with the remaining 6% consisting of wax and other additives. NTHE magic happens in the forming station, where this mixture is distributed onto a continuous steel belt in a controlled mat. The thickness is precisely regulated by leveling bars that ensure uniformity across the entire width of the production line. This mat then enters the continuous press, and this is where decades of engineering expertise really shine. The continuous press subjects the mat to temperatures of 400 degrees Fahrenheit and pressures exceeding 600 pounds per square inch. As the mat travels through this press, which can be over 100 feet long, the resin cures and the fibers bond together to create a panel that's denser and more stable than most natural woods. The precision of this process is remarkable. Temperature and pressure are controlled to within fractions of degrees and pounds per square inch. Now let's shift our attention to plywood production, which represents one of the oldest forms of engineered wood products. Plywood's story goes back over a century, but modern manufacturing techniques have transformed it into a product that's essential to contemporary construction. NTHE process begins with peeler logs, carefully selected timber that's been stored in hot water ponds to soften the wood and make it more pliable. These logs are mounted on massive lathes that can handle logs up to 8 feet in diameter. As the log rotates, a knife blade, sharpened to surgical precision, peels off continuous sheets of veneer, much like unrolling a paper towel. NTHE veneer sheets emerging from these lathes are remarkably thin, typically ranging from 1/8 inch to 1/4 inch thickness. The skill required to operate these peeler lathes takes years to master. The operator must constantly adjust the knife settings to account for variations in the wood, maintaining consistent thickness while maximizing the usable veneer recovered from each log. And after peeling, the veneer sheets move through dryers that remove moisture while preventing the wood from becoming too brittle. This is a delicate balance. Too much moisture and the glue won't bond properly. Too little and the veneer becomes fragile and prone to cracking. NTHE layup process is where plywood gets its legendary strength. Veneer sheets are arranged with their grain directions, alternating at 90-degree angles. This cross-grain construction is what gives plywood its superior strength and dimensional stability. Specially formulated adhesives, typically phenolic resins for exterior grades, are applied with precision coating equipment. NTHE invention of plywood represents one of the most significant advances in wood technology, with a history that spans over 4,000 years. Ancient Egyptians created the first laminated wood products by gluing thin sheets of wood together for furniture and sarcophagi. However, modern plywood as we know it was developed in the 1850s by Emmanuel Nobel, father of Alfred Nobel of Nobel Prize fame. The breakthrough came during World War I when aircraft manufacturers needed lightweight, strong materials for airplane construction. The famous mosquito bomber of World War II was built almost entirely of plywood, proving that laminated wood could outperform metal in many applications. What's scientifically fascinating about plywood is that the alternating grain structure creates what engineers call balanced construction. Each layer's grain runs perpendicular to adjacent layers, which virtually eliminates the wood's tendency to expand and contract with moisture changes. The adhesives used in exterior plywood are phenol formaldehyde resins that actually become stronger when exposed to moisture, creating bonds that can last for decades, even in harsh weather conditions. Modern veneer lathes are engineering marvels that can peel logs with mathematical precision. The knife pressure is controlled to within 2 pounds per square inch, and the knife angle can be adjusted to 1/10 of a degree. The most advanced plants use X-ray scanning to analyze veneer sheets for internal defects invisible to the human eye, automatically grading and sorting them for optimal placement in the final product. NTHE assembled layup then enters hot presses that apply tremendous pressure while heating the assembly to cure the adhesive. These presses, some as large as a small building, can handle panels measuring 4 feet by 8 feet or larger. The pressure and heat cycle is precisely controlled. Too much heat and the wood can be damaged. Too little and the bond won't achieve full strength. Quality control in engineered wood products involves testing that would impress any materials engineer. Samples undergo strength testing, moisture testing, and formaldehyde emission testing to ensure they meet strict industry standards. This attention to detail reflects the American manufacturing tradition of building products that exceed expectations and stand the test of time. What you're about to witness represents the pinnacle of American sawmill technology, a fully integrated system capable of processing 60,000 cubic meters of logs annually. This isn't just machinery, it's a symphony of engineering precision that would make the industrial pioneers of America's past proud while pointing the way toward our manufacturing future. Let's begin with the log feeder system, the gateway that controls the entire operations rhythm. Modern log feeders are marvels of hydraulic engineering, capable of handling logs ranging from small 6-inch diameter pieces to massive timbers over 30 inches across. The system uses photoelectric sensors to measure each log as it approaches, feeding data to the mill's central computer system that orchestrates every subsequent operation. What's remarkable about these integrated systems is their ability to process logs with 98% efficiency, compared to 60 to 70% efficiency in traditional mills of the 1960s. The computer systems coordinating these operations process over 10,000 data points per minute, tracking everything from blade sharpness to moisture content to energy consumption. Modern hydraulic systems operate at pressures that would have been unimaginable to early millwrights, up to 8,000 psi in some applications, yet with control precision measured in thousands of inches. The optical scanning systems use technology adapted from space exploration, employing laser interferometry to measure wood characteristics. These same principles help guide spacecraft to distant planets. NTHE Ester clamping trolley, type FHZSV, represents German engineering at its finest, adapted for American lumber production demands. This system grips logs with hydraulic clamps that exert over 50 tons of force, ensuring that even the most irregular logs are held securely during the initial breakdown process. The trolley travels on precision rails, positioning logs with accuracy measured in millimeters, a level of precision that would astound sawyers from just a generation ago. And at the heart of this operation stands the Esterer frame saw type HDSN, a machine that embodies over a century of sawmill innovation. Unlike traditional circular saws that remove wood as sawdust, frame saws use multiple straight blades moving in unison to make several cuts simultaneously. This approach wastes less wood, what we call kerf loss, and can process logs faster than conventional methods. The frame saw's blades are tensioned with the precision of violin strings, and they're sharpened using automated systems that maintain perfect blade geometry. NTHE Mehrhofer frame roller conveyor system that follows demonstrates how material handling has evolved into a science. These aren't simple rollers. Each one is computer controlled and can adjust its speed independently to maintain proper spacing between pieces. The system uses sensors to detect the size and weight of each piece, automatically adjusting conveyor speeds to prevent jamming while maximizing throughput. NTHE wide conveyor belt system for sideboards showcases the attention to efficiency that characterizes modern American manufacturing. Sideboards, those are the rounded edges removed from logs during the primary breakdown, were once considered waste. Today's mills recognize them as valuable raw material for secondary products. The sideboard removal table uses pneumatic systems to separate these pieces automatically, feeding them towards specialized processing equipment. Now, here's where the system's intelligence really shines: the S-conveyor configuration. These serpentine conveyor systems allow pieces to be sorted and directed to different processing stations based on their characteristics. Optical scanners read grade markings applied earlier in the process, and computer-controlled diverters route each piece to its optimal destination. NTHE Automatic Edger EWDDK 90 teraliters combines represents state-of-the-art optimization technology. This machine uses laser scanning to determine the best possible cuts for each piece, maximizing the valuable lumber recovered while removing defects. The Edger's computer makes these calculations in milliseconds, considering dozens of variables including grain patterns, knots, and market values for different lumber sizes. NTHE Meyerhofer length sorting system handles one of the most crucial decisions in lumber processing, determining the optimal length for each piece. Optical scanners identify defects, and computer algorithms calculate whether a piece should be cut at 8 feet, 10 feet, 12 feet, or longer lengths to maximize value. This decision-making process, which once relied entirely on human judgment, can now be made with mathematical precision. NTHE Esterer Resaw Type BNK 160 takes optimization to another level by reprocessing certain pieces to create higher-value products. This machine can take a 2x8 piece and rip it into two 2x4s if market conditions favor the smaller dimension, or it might remove a defect from the center of a wide board to create two clear, narrow pieces. Perhaps most impressive is the Springer sorting system with its 8-story configuration. This vertical storage system can simultaneously sort lumber by size, grade, and species while maintaining perfect inventory tracking. Each piece is tagged with a barcode, or RFID chip, that allows the system to locate any specific piece of lumber instantly. The automated stacking system that follows builds precise packages with stickers placed exactly where needed for optimal drying. Finally, the Rudnick and Enners chipping system ensures that absolutely nothing goes to waste. Every piece of wood residue, sawdust, shavings, and trim ends is collected and processed into uniform chips that become raw material for paper mills, particle board plants, or biomass energy generation. Modern chipping systems like those manufactured by Rudnick and Enners represent the culmination of decades of engineering focused on particle size optimization. The chips produced must meet exacting specifications, typically 3/4 inch in length with minimal fines, small particles, to be suitable for paper production. The disc chippers used in these systems rotate at speeds exceeding 1,000 RPM, with cutting edges harder than surgical steel. Modern mills achieve remarkable efficiency ratios, with some operations converting over 95% of incoming log volume into saleable products. The remaining 5%, mostly bark and ultrafine particles, is typically burned in high-efficiency boilers that power the entire mill operation, creating a closed-loop energy system that would have seemed impossible to earlier generations of lumber producers. This integrated system represents more than just technological advancement. It embodies the American spirit of continuous improvement and efficient use of our natural resources. Every component works in harmony with the others, creating a production environment where skilled craftsmen and advanced technology combine to transform logs into the building materials that construct America's future. NTHE 60,000 cubic meter annual capacity of this system means it processes enough lumber each year to build approximately 400 typical American homes. When you consider that this represents just one mill among hundreds across our nation, you begin to appreciate the scale of American lumber production and its vital role in our economy and way of life.